All right, next we're going to look at a class of puzzles that was very popular in the late 1800s. Now, in these puzzles, you have a grid of letters or numbers, and you got to slide the letters and numbers around to put them in order. And so as an example, here's the problem on a 3x3 grid or an 8 puzzle. You want to find a sequence of moves to go from this configuration. I'll do a 3x3 case. I got A here, B here, C, D, E, F. And I put G and H out of order. And that square's blank, and I can move tiles or letters into it. I want to start here, and I eventually want to get to the configuration where the letters are all in alphabetical order. So G and H are in order. Now, a legal move means you slide a letter into an adjacent blank square. And you can go in a row or a column. Okay, everybody understand the game? What you're supposed to do? You slide these things. That could go down. That could go across. How many people played the game like this before? Good, good, good. A lot of you. Okay, so I need some volunteers who are good at solving puzzles that can do this, have played games like this, that are pretty quick at it. All right? So I've got it here. All right, who'd like to come down? There's prizes if you can solve this. What we're going to do is solve this and see if you can solve it in 3 minutes. But I need 3 students to come on down and do this. Who'd like to volunteer? Who thinks they can handle puzzles under pressure? So you have the G and H out of order. See, it's not so hard. You move the F down there. I don't know. Play around like that. So I need some volunteers. Who'd like to come down and do this? You can win candy. I got candy here. There's even a prize if you don't make it in 3 minutes. Who wants some candy? Nobody? What's that? There is. Come on down. All right. Now, who's going to help him out? I need a couple more people here just to mess him up, because by himself, there we go. Good. Anybody else like to come on down? Because if we get 3, it really gets hard, because you fight over what moves to make. Now, what I'd like you all to do is sort of scream out possibilities for him. Like you figured out there, if you scream out, that'll really screw him up. Okay, so now you can't pick him up. You just got to slide him around. And you can go, and we'll go to 256 and see if you can solve it. If you can solve it, you guys get candy. And if you can figure it out there, let them know. No, you can't use the gray area. All right, you got about 2 minutes. Oh, they got the G and H in order. Everything else is pretty well screwed up, though. What do you got? A, B, C, D, E, F, H, G. No. That's where you started, guys. That's not it. It was close, yeah. Just one was out of order is all, but just one letter at a time. There you go. I think they need help. You got about a minute to go. You can't see anything. Well, I don't know if it would help. You want to show them where you are? This is not looking good. Yeah, we're pretty close to the end here, guys. ABC, FED, GH. GH is good. F is not so good. All right, you got about 30 seconds. Whoa. What are you guys doing? One at a time here. One at a time. In fact, I think time is up here. All right. All right, 256. Oh, no. That we don't do. No diagonal moves. No. All right, well, now you guys are good sports, so you do get a prize. It's not the candy, but I have these wonderful plastic Nerd Pride pocket protectors for you. There you go. Very good sports. Thank you. Well done. All right. Now, I was a little cruel to these guys. Can anybody, for a lot of reasons, it's impossible? You think? Yeah, it is impossible. This is impossible to do. Let's see if we can prove it's impossible. Because it doesn't seem so hard necessarily. But let's state that as a theorem. There is no sequence of legal moves. You know, diagonal moves makes this a lot easier. To invert G and H and also return all the other letters to their original order or position. Now, to prove this, we're going to use what's called an invariant. It's a very powerful and commonly used concept in computer science, very closely tied to induction, as we'll see. In order to show that your system can never reach a particular special state, it is sufficient to show there's some property called the invariant that holds at the initial state and that is preserved by every legal move, and is not present, does not hold in that special state. The idea is if you get this magic property called the invariant and it holds at the start and it holds across every step, then the only states you can reach have to have the property, the invariant. And if the special state doesn't have that property, you can't reach it. All right? So there is going to be some property we're going to look for that held at the beginning here. And the beginning had this setup. That holds, it's preserved by every move, every legal move, but does not hold in this state. And therefore, you can never reach this state legally. So they were doomed. So we got to figure out what that property is. And that's always the trick in analyzing systems or algorithms is what's that key property, the invariant property. So to figure out the invariant, we sort of have to look at what happens during a move in this system, a transition. Well, there's two kinds of moves. There's a row move. And an example of a row move is you might have A, B, C, D, G, E, F, H. And I'm going to move the G in its row to the blank square. So it would become this state. So G moves rightward into the blank, and the rest stays the same. Now, when I make a row move, did the relative order of the items change? No. In fact, of course, to be precise, I better define what relative order means, or the natural order. So by the natural order, I mean this ordering. 1, 2, 3, 4, 5, 6, 7, 8, 9. So if I look at the order here, G moved from 5 to 6, but didn't change its order with respect to any of the other guys. All right, let's state that as a lemma. Because that'll be very useful. Lemma 1. A row move does not change the order of the items, of the letters. Well, it's obvious. No, you can't let me get away with that, right? Because I'm not going to let you get away with that on homework. That's not so good. So we've got to be a little more careful in the proof here. Otherwise, we'll just head down the path to trouble. So let's sort of specify, what does a row move mean? Just get a little bit of math and specification around it. Well, in a row move, we move an item, a letter, from some cell I, whatever I could be anything, 1 to 9, into an adjacent cell What are the possibilities for the adjacent cell? Plus or minus 1, yeah. Okay, into cell I minus 1 or I plus 1. Nothing else moves. Hence, the order of the items is preserved. Because if you're going with I to I plus 1, everything else is in I minus 1 or less, I plus 2 or more. Relative order does not change in this case. All right, and I'll claim that's enough. All right, you know that I've thought about it a little bit. I've really quantified that I goes to I minus 1 or I plus 1. Nothing else moves. Therefore, we're done. Now, I could have added some more sentences here like I talked about, but this is probably enough in this case for this guy. So let's then look at in fact, if we only had row moves, there's not much that happens. The order never changes with row moves. So we never get there, but column moves are more interesting. So as an example of a column move, we have A, B, C, D, F, H, E, G. Say I move the G up. Then I would get this one. A, B, C, D, F, G, because G moved up, H, E. So G went to there. Did the ordering change for this move? Yeah. How so? What things changed order? Which pairs of letters changed order? G changed by 3, moved 3 in the order. And what letters did it change relative order with? Yeah, the two preceding it. G used to be after H and E. Now it's before H and E. All right, so it changed relative order with 2 items. It changed its position by 3, moved up 3 in the ordering. And so it changed order with the 2 in between.